Hello, today we'll continue our discussion of natural deduction with the initially puzzling topic of derivations without premises and its connection with the notion of logical truth. Then we'll conclude our lesson with a review of some of the ways in which we can use derivations outside of proving validity. Okay, let's talk about arguments with logically true conclusions. As we'll see, it follows from the respective definitions of validity and of tautology that an argument that has as its conclusion a logical truth is always valid, that is, independently of which premises we choose. Why is this so? Well, recall that an argument is valid if and only if it has no counterexample. And if you remember, a counterexample to an argument A is an assignment in which all the premises of A are true and the conclusion of A is false. This second condition is critical when we're talking about tautologies or logical truths. This is because when the conclusion of A is a logical truth, this second condition can never be satisfied, and thus there can be no counterexample. Therefore, when its conclusion is a logical truth, argument A is valid, regardless of the content of its premises. And this leads us to an important fact, namely that a logical truth is entailed by any set of premises. For instance, take this argument: roses are red, violets are blue, therefore the sun will explode tomorrow or it won't. The conclusion is a logical truth, since it is of the form X or not X. So it's impossible to find a counterexample for this argument, because a genuine counterexample would make the conclusion false. But there is no way for this conclusion to be false. Hence, by default, it's valid. And as a matter of fact, it is even sound. However, the premises play no part at all in the validity of this argument. If we substitute premise 2 by an obviously false statement, like number 2b, the present great Khan of the Mongol Empire is Taylor Swift, that doesn't affect one bit the validity of the argument. It's still valid. In sum, the two arguments we just saw are valid, though in an admittedly strange way, since they are not valid in virtue of the premises, as these contribute nothing at all to the argument's validity. Instead, the weight of their validity rests entirely on the shoulders of the conclusion, and it is due to the fact that the conclusion is guaranteed to be true. How does this fact about validity affect those derivations that have logically true conclusions? In this way, whenever a tautology is the conclusion of an argument, the premises are unnecessary. Thus, in a derivation corresponding to such an argument, the premises may not be used at all. A tautology, then, can be established with no premises whatsoever. In sum, a logical truth is entailed by the set with no premises. And what is important for our present topic, a logical truth is derivable without any premises. But you may be asking, if we don't use any premises, how do we get our derivation started? This feels a bit like pulling yourself up by your bootstraps. So what do we do? Well, instead of using premises, we have to rely on assumptions, along with the rules that are associated with them. These are, of course, the subderivational rules, to wit, conditional introduction, negation introduction, and the derived rule RD, or reductio ad absurdum. An example: consider an argument that has only one premise, C, and its conclusion is if A, then A or B. Notice that this conclusion is a tautology. You can test it out yourself. In the corresponding derivation of the conclusion, C is the only premise. On line 2, we introduce an assumption. On line 3, we apply one rule. We discharge the assumption and close the subderivation. And in the outer derivation, we write if A, then A or B. Well, let's focus on the subderivation in lines 2 and 3. This is a perfectly legal derivation, but it makes no use whatsoever of the premise in line 1. The same will happen if we substitute C with any other set of premises. If instead you choose D, the derivation still works. And if you choose E, the derivation still works. You can go through the whole alphabet and nothing will change. In fact, given that premises make no difference at all, we can leave them out altogether. We would have a derivation from the empty set, or the set with no members. This illustrates that a logical truth can be derived with no premises at all. Thus, a derivation with no premises has as its conclusion a logical truth. Moreover, this suggests a procedure for showing that a sentence is a logical truth. To show that a sentence X is a logical truth, or tautology, we provide a premiseless derivation of X. And this is because this procedure only works with logical truths. Suppose that we want to derive a contingent sentence like if A then B. Then we have to choose the appropriate premises. Let's say that we pick B and C. Then we can indeed derive if A then B from B and C. Again, the conclusion comes from a subderivation, which occurs on lines 2 and 3. But this time, the subderivation does make use of the premise, as you can see on line 1. So the premise is doing work. If you substitute, say, D for B in line 1, the conclusion doesn't go through anymore. So it's only in the case of logical truth that premises don't matter. Okay, with this in mind, let's show that this sentence is a tautology. So our conclusion is a conditional, but notice that it has more than one horseshoe. But there is one horseshoe that is the main connective and that divides the sentence in two parts. One that is the antecedent and which we mark with an X, and the other one which is the consequent, which is Y. So we're going to use horseshoe introduction to prove this conditional. So the assumption is going to be the antecedent. But notice here that we have two scope lines, and that is because from the beginning we're starting with a subderivation. We don't have any premises. So we begin with the antecedent with the assumption, and then as always the goal of the subderivation is going to be to prove the consequent, which in this case is D. So the goal of the subderivation is going to be to show D. And then by using our rules, we get D. And then we close our subderivation and introduce the desired conclusion from lines 1-4 by horseshoe introduction. But notice that we didn't use any premises here. Therefore, the sentence that we're concluding here is a tautology. Now, we often use conditional introduction when we're dealing with conditionals, but we can also use other rules for other kinds of sentences. For instance, we can use those that involve negations, such as negation introduction and reductio ad absurdum. To see why they can be useful, just bear in mind the following fact. The negation of a tautology is a contradiction. So, suppose that you have a sentence X and that you transform it into its negation, not X. And not X turns out to entail a contradiction. Then X is a tautology. So we're going to leverage this fact to show that this sentence is a tautology. We're going to show that if we negate it, we end up contradicting ourselves. So let's show that this sentence is a tautology. So we start by assuming the negation of the sentence, and then what we want to end up with is a contradiction. So we start with an assumption, which we write by putting everything in parentheses and adding a tilde in front. So I'm alternating brackets and parentheses here, but that's just for clarity. Nothing hangs on this. So we start with our assumption, and then our sub-goal is just going to be to get a contradiction, X and not X. So we apply our rules, and then we notice that on lines 4 and 7, we get not B and B. So we can discharge our assumption, right? Our next step is to close the subderivation, and on line 8, we can get rid of the main negation sign. Justification is reductio ad absurdum on lines 1 through 7. So we can conclude that this sentence is a logical truth. There are other uses of derivations. For instance, we can use derivations to show that a sentence is a contradiction. In general, if a sentence X is contradictory, that is a logical falsity, then you can validly derive Y and not Y using X as the only premise. So, to prove that X is a contradiction, we show that Y and not Y are derivable from X, taken by itself, or Y can be any sentence. In the handout, you'll get a more complete explanation of how you get to this point, so you can read it there. So let's show that this sentence is a contradiction. Then our task is going to be to construct an argument with the sentence in question as the only premise, and Y and not Y as its conclusion. So we're going to build a derivation, and then our only premise is going to be the sentence, and then our ultimate goal is to get just any contradiction. So we apply our rules, and we notice that on lines 3 and 6, we get not B and B. So to comply with the definition, we construct B and not B by conjunction introduction in 3 and 6. So we have shown that this sentence is a contradiction. What about inconsistency? Well, it's something very similar. Remember that a set of sentences is inconsistent if and only if there is no assignment in which all of its members come out true. And in fact, contradiction can be seen as a special case of inconsistency, namely one in which the set of sentences has only one member that can never be true. And so trivially, there is no case in which all of the set members are true. Likewise, the procedure for showing inconsistency is essentially the same as that for proving contradictoriness. Namely, to prove that a set S of sentences is inconsistent, we show that both Y and not Y are derivable from the set of premises comprised exclusively by the members of S. Y can be any sentence. Let's do an exercise. Show that the following set of sentences is inconsistent. So we have a set here with 3 members, and we line them up as premises of an argument. And our goal is going to be to get a contradiction. So we apply our rules, and we notice that on lines 6 and 7 we have A and its negation. And so on line 8, then we should write A and not A by conjunction introduction. I'm going to skip this step. The point is that this set of sentences is inconsistent because they jointly entail a contradiction. Equivalence. We can also use derivations to show that 2 sentences X and Y are equivalent. To do so, we must show that each sentence is derivable from the other. Thus, we have to provide 2 derivations, most of the time at least. We have to show that Y is derivable from X, and we have to show that X is derivable from Y. But with one special case. When you have a derivation that only makes use of equivalence rules, or 4-dot rules, as we also call them, one derivation is enough, since we know that these rules work in 2 directions. In this case, if we can run a derivation downwards, we can also run it upwards. However, if you have even one application of a 3-dot rule, then you have to provide 2 derivations, one in each direction. Let's show that these 2 sentences are equivalent. Sentence A and sentence B. Our initial setup then is first an argument from A to B, and then we flip them, and then we have an argument from B to A. Those are our 2 steps. Okay, let's begin the first part. Here we have sentence A as premise and sentence B as the conclusion. Well, sentence B, our desired conclusion, is a conditional, so we're going to use conditional introduction. And as always, we use the antecedent as the assumption. And again, as usual, we're going to aim at proving C, which is the consequent of the conditional. So our sub-goal is going to be C. So we apply our rules, and I'm not going to go step by step because you already know this. But the idea is that on line 7, we were able to get C. So we reach our sub-goal, and we can close our subderivation, discharge our assumption, and we conclude then sentence B by conditional introduction. So our first phase is done. Now let's go to the second. We have sentence B as the premise and sentence A as the conclusion. Again, sentence A is a conditional, and so we can begin using as an assumption its antecedent, not A. And then our goal in this subderivation is going to be B or C, which is the consequent. So I write not A, and I'm writing down here assumption for conditional introduction because I'm going to employ another subderivation. So notice that now we have to get B or C. Well, one straightforward way of getting B or C is by reductio ad absurdum. Remember that any sentence that implies a falsity is itself false. Therefore, if not X implies a contradiction, then not X must be false, and in consequence, X must be true. So one strategy then, show B or C, is that we're going to assume the negation of B or C. Then we're going to reach a contradiction, and that will allow us to say that B or C must be true, because its negation is false. So we start not B or C, and it's going to be our assumption for reductio ad absurdum, RD. So this is a new subderivation. And again, our goal is going to be any contradiction, and this will allow us to get rid of the tilde. Okay, so we start to apply our rules, and notice as a point of strategy, and these are the sort of things that you should be on the lookout for, that on line 1 we have C, and on line 4 we have not C. This is probably the source of the contradiction that we're going to use. So I'm going to try to detach C from 1 and not C from 4. So on line 8, I'm able to get C, and then from line 4, I'm able to get not C. So I got my contradiction, and by reductio ad absurdum, I can obtain B or C. But automatically, you see that I've just obtained the goal of the first observation. So I can close that too. And then I can conclude that if not A, then B or C by conditional introduction, lines 2 to 10. So the argument from A to B is valid, and the argument from B to A is also valid. Therefore, these two sentences are equivalent. So let's do a summary of the uses of derivations. We know that to show that an argument A is valid, we derive A's conclusions from its premises. To show that a sentence X is a tautology, we derive X without any premises. To show that a sentence X is a contradiction, we derive Y and not Y from X alone. To show that a set S of sentences is inconsistent, we derived Y and not Y from the set S alone. To show that two sentences X and Y are equivalent, we derive Y from X and X from Y. And what about the rest? Validity, consistency, contingency, and inequivalence. Well, those will be the topic of our next video. Goodbye.